we now want to look at standard derivatives. I want to emphasize here, please, that all the standard derivatives you're going to see henceforth, you are expected to memorize them. Once a problem is given to you, you apply it, anyone that works for that problem or any of the function given to you. The first we have on the board is polynomial function. A polynomial function is one in which the variable is raised to a given power. The power is a number, as the case might be. You can see that here. This is y equal to f of x raised to the power n. N can be whole number, it can be a fraction, it can be positive, it can be negative. How do you differentiate it? Look at it, you start with a major differentiation. Of course, you can also do the minor first, but all the same. Here, the major is this power, because it is this power that defines polynomial function for us. Is that okay? So you're going to use the power to multiply this function of x. Can you see that? Then go to the power and subtract 1 from it. When you are done with that, multiply it. This time around, go and differentiate the minor, which happens to be the function of x there. Is that okay? So you can see it, differentiate the f of x with respect to what? X. That is the f of x over the x. So that is the interpretation of the major minor concept. Let's quickly look at this for you to understand this. Imagine you're given an example here that y is equal to, let's say, x raised to the power 3 plus 5, and then everything raised to the power 4. You are to obtain your dy dx. How do you proceed? My dy dx is equal to simply identify your major and minor. This is the major, because that is what really defines this bracket as a polynomial function for us. And our minor is this function of x. Take note, everything in this bracket there is function of x. In fact, this 5 that is a constant is also a function of x. It is the same as 5x raised to the power 0. Is that okay? Anything raised to the power 0 is 1. 1 times 5 will still give you 5. So this bracket is a function of x. Now to differentiate, you start with this 4 outside, which happens to be our n. Here is going to be 4 times the whole function of x here. You can see f of x, which is x cubed plus 5. Then subtract 1 from this power. If you subtract 1 from 4, what will you get? 3. Now this time around, we're going to differentiate the minor function, which is x cubed plus 5. We will differentiate this x cubed. If you differentiate it, it's a polynomial as well to x raised to the power 3. You're going to use the power 3 to multiply that x and then minus 1 from that power 3, which will give us what? 2. Then plus this 5 here is a constant. We said it already. If you differentiate a constant, you get what? 0. So you see, this is the major function derivative. This is the minor function derivative. All you need to do is to solve out now. This bracket is the same as 3x squared, because plus 0, the 0 is nothing. So this 4 will multiply this 3x squared that is here, and then you will get what? 12x squared times x cubed plus 5, everything raised to power 3. Take note that this power will not allow you to open up this bracket with this number outside here. Hence, this is our solution using the major minor function differentiation concept. So now we want to look at the second function, okay? And I want to get a standard derivative of that function. It happens to be exponential function. Exponential function is represented with the symbol e. So if you have y equal to exponential f of x. Now this f of x is our minor function. And then our major function is what? The exponential. So what do? Major minor differentiation. Now we're going to differentiate a minor, then times differentiate the major. Or it's still the same as differentiate the major first times differentiate the minor. I decided to do the minor first, okay? That's what I always like, doing the minor first. So you can see that dy dx is now equal to, want to differentiate this. So it's going to be the f of x, that is the derivative of the minor over the x, then times you differentiate the major. If you differentiate an exponential function, you still get exponential. So take note of that. That is why the major function differentiator still gives us exponential of what it is carrying. Is that okay? So let us apply to a question here. You can see these 2 examples. I'm going to be fast. Y is equal to exponential minus x squared. What is our minor? This is our minor minus x squared. Is that so? And then our major is what? Exponential. So we're going to differentiate minor and then differentiate major and multiply them. If you differentiate a minor, which is minus x squared. Minus x squared is a polynomial function. Is that so? So the derivative of this minus x squared will give us what? Minus 2x. Remember, minus x squared differentiated is the same as use the 2 to multiply minus x and then subtract 1 from the power. If you subtract 1 from 2, you're going to get 1, which is still the same as this term. So 2 times minus x will give us minus 2x. Is that okay? Then multiply by the derivative of the major, which is exponential. If you differentiate exponential function, you still get what? Exponential of what it is carrying as a minor function. Is that okay? So this becomes the result. Now let's quickly look at this one. Y equal to exponential 5x plus 4. It's still the same thing. Our minor is this, and our major is what? This exponential. So differentiate a minor, which is 5x plus 4. If you differentiate 5x plus 4 alone, remember that 5x plus 4 is a polynomial function. Differentiate this 5x. If you differentiate this x alone, you get 1 times this 5. You have your 5. If you differentiate this 4, is a constant, you get 0. Is that not so? So the derivative of this 5x plus 4, the minor function will give us 5. You can see that here. Then differentiate the major. If you differentiate the major, which is exponential, what did I say already? Derivative of exponential will still give you what? Exponential of the minor function that it is carrying. Therefore, this is a result of this derivative of this function. Alright, now let us consider the standard derivative of trigonometric functions. Okay, on the board here you have that of sine and cos. So if you're giving y equal to sine f of x, how do you differentiate? It's very simple. Remember our major and minor function. The minor is f of x and the major is what? Sine. So all you need to do is to differentiate the minor. You can say that dy dx is equal to differentiate f of x with respect to x. Then times differentiate the major. If you differentiate sine, you get what? Cos. Cos of the f of x, that is the minor function it is carrying. That's quite simple. Alright, now coming here, just let's look at this example. Y is equal to sine 3x. So what do you do? This is our minor, this is our what? Major. So you do your minor major differentiation, differentiate 3x. If you differentiate 3x, remember that this is a polynomial, is that not so? So you use polynomial function rule to differentiate this x, you're going to get 1. 1 times 3 will give you this 3, you can see that, right? So 3 is the derivative of this minor function. Then proceed and differentiate the major, which is sine. Differentiate sine, you get what? Cos. It's now going to be cos of the 3x. Look at another example. Y equal to sine x squared plus x. This is our what? Minor function, and this is our what? Major function. Differentiate your minor times differentiate the major. Your problem is solved. The minor here is x squared plus x. If you differentiate this polynomial function, you know that? You're going to get 2x plus 1. This is it. Then times standard derivative of the major function, which is sine, it will give you what? Cos. Cos of the original minor function. And that's the result. So we look at that of cos f of x. If you differentiate cos, you're going to get minus sine as a standard. So this is our major, our minor function, rather, that is f of x, and this is what? Our major. All you have to do is still similar, differentiate your f of x with respect to x, that is minor function, then times standard derivative of the major function cos. If you differentiate that, you get what? Minus sine of the original minor function. Now, look at an example here. Y equal to cos x raised to the power 4. This is our minor, and then this is what? Our major. So differentiate your minor, which is x raised to the power 4. Is a polynomial again, you're going to get 4x raised to the power what? 3. Then times standard derivative of cos, which is what? Minus sine. Minus sine of the original minor function. And of course, if you multiply this, you get minus 4x cubed sine x raised to the power 4. So you see this, you don't need to punish yourself, say let u be equal to this and that. It's not necessary. You get your result just in 1 or 2 steps, as the case might be. Now, make sure you follow this pattern, understand the others that you're going to see, or that is other trigonometric function is very similar, and of course, it's quite simple. Alright, in this video, we now direct our attention to a function called the logarithmic function. We're going to consider two of them, logarithm to base e, is that okay, which we call ln, or log to base e. This ln and log to base e, they are the same thing. And then the second is logarithm to a constant base, a. In this case, this a is a number which is not this exponential base again. Now, how do we go about the standard derivative? You have them on the board. If you're giving y to be equal to ln f of x, okay, y to be equal to ln f of x, how do you differentiate that? Now, let us look at it. Remember our major minor concept. So our dy over dx is going to be equal to differentiate the minor function, which is f of x, with respect to x. Then times differentiate the major function. You can see now, right, that the major function, which is ln here, if you differentiate it, what are you going to get? 1 over what is in front of the ln. So take note of that. Standard derivative of log to base e, which is also called ln, is simply what? 1 over what is in front of it. Now, let us consider an example here. We have y to be equal to ln x, and we are to obtain the differential coefficient dy dx. What's now going to be our answer? here our f of x, which is the minor function, is x. So we're going to differentiate the x. If you do that, you get what? 1. Then times standard derivative of the major function ln, which we said is what? 1 over what is in front of it. So it's going to be 1 over x. Solving that out, you have 1 over x as your answer. Now let's quickly consider the second example. In this case, you're giving y to be equal to ln sine x. You have to obtain the derivative of this y. So what do? Identify your minor function, which is sine x. Differentiate sine x, you're going to get what? Cos x, you can see it. Then times, you now move on to differentiate a major function, which is ln, and if you differentiate ln, you get what? 1 over what is in front of it. So it's going to be 1 over sine x. Working this out, cos x times 1 will give us cos x divided by sine x. And from the study of trigonometry, okay, we talked about trig identity. Cos x over sine x is equal to a trig function called cot x. It's an inverse of tan. Is that okay? Now, let us move on to the second one, that is logarithm to a constant base a. How is it written? You can look at it. Y is equal to log f of x base a. A can never be 0. Take note of that. In fact, it can't even be a negative value. It's usually positive. So how do we go about that? dy over dx is now equal to, you differentiate the minor function as usual, our f of x with respect to x. Then times what happens now to differentiate the major function, which is log to that base a, is going to be 1 over what is in front of it, which is f of x, times ln the base, which is ln a. Now we're going to look at an example here to interpret that. Y is equal to log x raised to the power 2 base 7. Now how do you solve that? Our minor function is x squared, is that not so? And the major function is log base 7 there. So dy dx is now going to give us equal to differentiate the minor function x squared, you're going to get what? 2x. Then times 1 over that x squared, like f of x, are you saying that? Times ln a, where your a here is what? 7. You are done with that. The next thing is just to simplify further. If necessary, 2x times 1 will give us 2x divided by x squared ln 7. And of course, you know that this x can cancel out 1 here by dividing. You'll be left with 1x in the denominator. The numerator will be 2 all over x ln 7. We now look at the general exponential function derivative. When we talk about the general exponential function, it's something that looks like this. You know, our usual exponential function, like we learned before, so you have y equal to exponential, maybe f of x, is that not so? Where in that case, you notice that we have the exponential as e, all right, the natural base, okay, carrying the power. But in this case, being the general exponential function, the base now is what? A, where a is a constant, which is not 0. It can be any other number, as the case might be. So we refer to this as the general exponential function. How do we differentiate that? The standard derivative, you can see that. Just watch carefully. You still follow our major minor concept, alright? The minor function is the f of x as the power of a there. So you can see that differentiate that f of x with respect to s, then times. We now come to the standard derivative of that term there, raised to the power f of x. How do we handle that? It's going to be the a raised to the power f of x. That is that same term. Are you getting me? Exactly. Then times ln of the base, the constant. Are you following? That's ln a. We're going to apply these to solve these two examples. Let's look at it and see how it works. Now, y is equal to a raised to the power what? X. Okay? So how do we obtain the y dx? You differentiate the minor function, which happens to be x here. You're going to get 1. Then times, you move on here and differentiate this a, okay, raised to the power x there. And what will it be? Looking at the way we arranged it here, it's going to be this same term. That is a raised to the power x. You can see that here. Then times ln a, that is ln of the base. Therefore, this becomes the answer, a raised to the power x ln a, if you multiply it with this one here. Now let us consider this one a bit complicated, but not difficult, okay? We can still use the same principle. Y is equal to a raised to the power 5x squared. Now we have to obtain the differential coefficient dy dx. What do we do? Identify your minor function, which is 5x raised to the power 2. If you differentiate that, you're going to get 10x. Then times standard derivative of this term here, which is going to give us what? That same whole term, which is a raised to the power 5x squared, times what? Ln the base, that's ln a. You can see that here. Alright, this is the final answer I decided to write. I just rearranged this. Remember, multiplication does not respect order of arrangement, so I decided to bring a raised to the power 5x squared backward and then 10x forward. Okay, then ln a is still the same thing. Look at this very carefully, please. Okay, the function still to be memorized is standard, and so when you see any problem of this kind, you can use it to handle the question. Alright, you want to have fun with this one on the board now, okay? We are asked to find dy dx, where y is equal to 2 raised to the power x raised to the power 5. Now, how do we approach this problem? If you look at it, it might seem a bit Okay, terrifying or complex, but hey, it's 1 plus 1, nothing is there. All you need to do is to identify the form of function this thing is. Looking at this is 2 here, it's a constant, so it represents our a. So we've identified a to be equal to 2. It therefore means that this follows the general exponential function derivative pattern. Alright, now I quickly have to recall that we know if y is equal to a raised to power f of x, to obtain our dy dx, what do? This is standard. You're going to differentiate a minor function, which happens to be f of x, then multiply by that same function itself, a raised to power f of x, and then finally multiply by what? Ln of that constant base, a. And so we're going to use that to solve this problem. So for y equal to 2 raised to power x, and then raised to power 5, how do we differentiate that? Okay, let us quickly identify our minor function to be x raised to power 5, so we're going to differentiate that, okay? If you differentiate x raised to power 5, what are you going to get? 5x raised to power 4. Then multiply it by this whole thing itself, which is 2 raised to power x raised to power 5. And then finally what? You multiply by ln of the base, which happens to be 2. You're done. The next thing, if you want to simplify further, is your choice. There is no much simplification here. Like what I did is just to rearrange as usual. I prefer writing this one carrying power. I prefer writing it first, okay? Then followed by this and then ln 2. That's just anything I did here. I decided to label some things here to tell you that this term is derivative of the minor function and this whole thing is derivative of the major function. Alright, this brief note on the board here is very important, please. So don't be confused to go and multiply these 2 by 5. It's not possible, alright? It's not possible because of this x raised to power 5. Okay, this is our result. In this video, we consider another function that is called the hyperbolic function. It is very similar to trigonometric function. Okay, now the first one I want to consider here is y equal to, it's pronounced shine f of x. Is that okay? So it has something like shine, cosh, tang, shake, coach, and alright, now let's just look at it. For y equal to shine f of x, to differentiate what is going to give to us, dy dx is equal to differentiate the minor function, which is f of x, and then times differentiate the major function. If you differentiate shine, you will get cosh of f of x. You see, it's much similar to something you saw on the trig, where you differentiate sine to get what? Cos. Now this h here means hyperbolic. So this is actually, besides the normal pronunciation which you heard shine this, it really means hyperbolic sine. Is that okay? Now let us look at the question here. We have y to be equal to shine 3x squared, and then you are to obtain dy dx. Okay, so we're going to identify our minor function and differentiate it. Is 3x squared. If you differentiate that, you're going to get 6x. And then differentiate the major function, which is shine. If you differentiate that, you're going to get what? Cosh. It's going to be cosh of the minor function. So that's cosh of what is in front of the original function given here. So this is 6x cosh 3x squared as our result. Now let us look at the next function there. That is cosh f of x. If you're given y to be cosh f of x and then you're to obtain the y dx, it's going to be differentiate the minor function, the f of x dx, then times standard derivative of cosh, which happens to be shine. If you differentiate cosh, you get shine f of x. Is that okay? Please, you need to be careful here. If you take note, there is nothing like minus shine. Under trig, if you differentiate cos, you get what? Minus sine. It does not apply for hyperbolic. If you differentiate cosh, it's going to give you positive shine, alright? Now we have an example here. Y is equal to cosh 2 open bracket x squared plus 2 close the bracket raised to power 4. We have to obtain dy dx. What do? Identify your minor function, which happens to be 2 bracket x squared plus 2 all raised to power 4. If I give you this term alone to differentiate, how do you do that? Of course, you agree with me, it's going to be start from the major term outside, which defines the polynomial for us. It's going to be 4 times this 2, which will give us what? 8. Is that not so? Bracket x squared plus 2, close your bracket and subtract 1 from it. That's the kind of saying 4 times 2, open bracket x squared plus 2, then 4 minus 1. That's what gave us this part. Then multiply it by this time around, you differentiate a minor function of this term again. Inside this term, look at it, you have major and minor, the major being this one, the minor being this function of x. Remember your polynomial differentiation. So having differentiated from the outside, you now move inside and differentiate the function of x, that is x squared plus 2. If you differentiate the x squared there, you're going to get what? 2x, look at it. Okay? If you differentiate these 2, it will give you 0, so it will go away. Derivative of the constant is 0, it's going to go away. So that's how we got this term here. Then it is now time to differentiate the main major function there, which is cosh. If you differentiate cosh, you get what? Shine. is going to be sine of the original thing given to you in front of the card from the question, which is 2 bracket x raised to the power 2 plus 2, close it, raised to the power 4. Simplifying this further, 8 times 2x is going to give us 16x, then times this bracket raised to the power 3, sine 2 times this bracket raised to the power 4. Take note that this bracket cannot be opened with this 16x, reason because of this power 3. Alright, so we want to look at the c function, right, of the hyperbolic. It happens to be the tang. Y is equal to tang f of x. Now, how do you go about that? Still your major minor, you can look at it, df of x dx times standard derivative of this tang will give you sec square. Alright, so sec square f of x. If you take your mind back to trig, when you differentiate tan, what do you get? Sec square. So here you differentiate tang, you get sec square. It's all about introducing your h, which represent the hyperbolic. So now, this is an example. Y is equal to tang x. You have to obtain the differential coefficient, the y, the x. So what do? Identify your minor function, which is x, and differentiate it. You're going to get 1 times standard derivative of the major function, which is tang. If you differentiate the tang, you get sec square x. That is sec square what is in front of a. And of course, 1 times this sec square x will give us what? Sec square x, which means that the derivative of tang x will give you sec square x. In this video, we are going to look at standard derivatives of circular inverse function. When we talk about circular inverse function, we are referring to the inverse of trig functions like sine inverse, cos inverse, tan inverse, cot inverse, sec inverse, and the rest of them. But we're going to consider just 3 of them: the sine inverse, the cos inverse, and the tan inverse. Quickly on the board, we have these: y equal to sine inverse of f of x over a. GMAT 41 decided to use this standard, alright, in order to cover the general knowledge of what you need to know about circular inverse function. In most cases, you will see y equal to sine inverse of x, therefore the y dx is equal to 1 over square root of 1 minus x squared. It doesn't work in our case, so we are using a general knowledge in order to help you out, so that for whatever question you're given, using our general standard here, it's going to solve your problem for you. So we have this first y equal to sine inverse of f of x over a. This a here is a positive integer. Is that okay? It's a number. And now, how do we approach the differentiation? So watch. The y dx is equal to, using our major minor still, in this case, the minor function is this f of x, the numerator there. Please don't touch the denominator, which is the constant there. Is that okay? So we're going to differentiate this f of x with respect to x. Then times, you now move on, standard derivative of sine inverse is going to give us 1 over square root of a squared, that is square of the denominator here, minus the numerator f of x squared again. So you can see that this is the standard. Now we're going to use it to consider these 2 examples here on the board. We are told to obtain dy dx for y equal to sine inverse of x. So what do? Now if you look at this problem, you'll agree with me that our a here is 1 because it's the denominator of this x. It's invisible 1. Is that okay? Invisible 1. That's what our a is there. And then, so if we are to differentiate, now what do? Dy dx equal to, we differentiate the numerator minor function of x, which happens to be this x here. Are you getting? So if you differentiate this x, you get 1, then times standard derivative of this major function, sine inverse, which is 1 over square root of a squared minus f of x squared. What is our a here? I said earlier that it is an invisible 1. A here is invisible denominator 1. So it's going to be 1 squared using the standard minus f of x squared. Our f of x is the numerator, the function of x there. So you're going to square it, everything as numerator there. So it's going to be x squared. If you simplify this, sine inverse of x will give us 1 over square root of 1 minus x squared. Now let us quickly look at this example again to help you to appreciate this standard that we've just brought out to you. Y is equal to sine inverse of x squared over 3. Now I'm going to ask you a question. What is the numerator function of x here? You'll agree with me it is x squared. Is that not so? And what is our a here? You'll agree with me that here our a is equal to what? 3. Good. We're now going to use this standard to solve the problem. The first thing we differentiate to obtain our dy dx equal to differentiate the numerator minor function of x. Our x squared is our f of x here. So if you differentiate this x squared, you're going to get what? 2x. Then times standard derivative of the sine inverse. If you differentiate sine inverse, we've said that already, you're going to get 1 over square root of what? A squared minus f of x squared, where a is the denominator, constant number, so you're going to have 3 squared minus f of x here is this numerator x squared, you have it there, then square everything following this standard. Simplifying this further, 2x times 1 gives us 2x all over square root of 9 minus x raised to the power 4. How did we get this x raised to the power 4? If a term is carrying 2 or more powers, according to parallel law of indices, all you need to do is to multiply the powers out. So that's how we got this result. Derivative of cos inverse. It's very similar to that of sine inverse, only negative separates them, okay? Now we have this example on the board, okay? We're going to use it to explain the concept of derivative of cos inverse. Now we have y to be equal to cos inverse of 5x cubed all over 4. If we are to obtain the y dx, what do we do? That is the differential coefficient. Remember the standard for cos inverse, we said it's negative that of sine inverse. If you have maybe y to be equal to cos inverse of f of x over a, then dy over dx was said to be equal to the f of x over dx, then times minus 1 all over square root a squared minus f of x. Alright? Everything squared. So we're going to use that standard to solve this problem. Dy dx now is going to be what? We'll differentiate the numerator minor function. Look at it. We'll differentiate it. And so the 5x cubed, if you differentiate it with respect to x, what will you get? It's going to be 15x squared. You should take note of something here. I didn't touch the denominator. The denominator in this case is a, which is 4, alright? We're going to use it once it is its turn to be used. So this will be times minus 1 all over a squared, that is in square root here, a squared, and our a is this 4. So it will become 4 squared minus f of x squared. All this numerator term here is our f of x. So it's going to be 5x cubed, then all squared. Does it make sense? Let's simplify this. You're going to have 15x squared times minus 1 will give us minus 15x squared all over square root. Then 4 squared is 16 minus, if you open up this bracket with this square outside, it's going to be 5 squared, giving you 25. Then x cubed squared will give you x raised to power 6. Remember, for your indices law, power can distribute over multiplication. If I have xy raised to power a is equal to x raised to power a times y raised to power a. So that is why this square affected this 5 to give us 25. Then x cubed, it affected this because this x is carrying power 3. Multiply the power, you have 6. Of course, this is our dy dx for this problem. Pretty simple, okay? Alright, we are going to look at this example on tan inverse, okay? But the tan inverse standard derivative, we have it on the board here, giving y to be equal to tan inverse of f of x over a, and then you have to obtain the y dx. How do you get it? First of all, you do the f of x, that is differentiate the numerator minor function with respect to x, and then multiply by standard derivative of the major function, which is tan inverse. The standard derivative of tan inverse is what? A over a squared plus f of x squared. Take note that in this case there is no square root in the denominator again, so don't confuse it with that of sine inverse on cos inverse where you have square root in the denominator. Is that okay? Having said that, this is the standard of tan inverse. Remember, our a is the denominator constant of what? F of x. Just imagine this case, this example, tan inverse of x. Did you notice that a here is what? An invisible one in this case. Our f of x is this x. So if you work around that to get your dy dx or tan inverse of x, it's going to give you this, because in that case a is what? Invisible 1 here, all over a squared, which is 1 squared, plus f of x squared, which in this case our f of x is what? This x. So you square. Alright, you can just go through that quickly. Let's focus on this and solve together, alright? Y is equal to tan inverse of, open bracket, 1 minus 2x squared, close your bracket, all over 3. Obtain the differential coefficient of y. When you hear differential coefficient, it means dy dx. Getting that is very simple. Dy dx, going by the standard, we are going to differentiate the numerator minor function with respect to x. And the numerator minor function is 1 minus 2x squared. If you differentiate this one here, you get what? 0. It's a constant. Derivative of a constant is 0, so it goes off. Minus 2x squared, if you differentiate it, what will you get? You get minus 4x. And then multiply it by the standard derivative of this major function, tan inverse. If you differentiate tan inverse, what will you get? Remember, a over a squared plus f of x squared. Where in this case our a is what? Consider that our a is equal to 3. And so it's going to be 3 over 3 squared plus, open bracket, square of the numerator minor function f of x, which is 1 minus 2x squared, close it, and then it's squared. That's that. All you need to do is just to simplify further. If possible, we're going to have minus 4x times 3, which is minus 12x, divided by 3 squared is 9, plus, when you come here, it's not usually ideal to expand it. It's not usually ideal to expand. So take note, which means you're going to write 1 minus 2x squared all squared. If you must expand it, of course, you know, you have to multiply 1 minus 2x squared by 1 minus 2x squared. But like I said, in most cases, it's not necessary expanding it if you have a term of this kind. So this is the dy dx, or differential coefficient of this problem.